All right, let's look at example 2 here. It says, which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So they give you an excellent picture here to look at it. Here's the point 0, 2. Here's the parabola of 4 minus x squared. So the question is what points on that graph are at minimum distance? And we know it's going to be 2 because the axis of symmetry is x equals 0. So whatever it is on the right, it's going to be the same thing on the left, just the negative x value. So what are we trying to do? We're trying to find the closest point. So what are we trying to minimize? Well, technically, aren't we going to minimize the distance? And aren't we minimizing the distance between the point 0, 2 and whatever points on the graph? So what I need to minimize is the actual distance formula. And if you remember, what is the distance formula? It's the square root of x2 minus x1 squared plus y2 minus y1 squared. Technically, just to let you know, comes from the Pythagorean theorem. A squared plus b squared equals c squared. So in this case, this is the distance between, well, we know what one of our points is. The point is 0, 2. So it's really going to be x minus 0 squared plus, and then it's going to be y minus, my y value is 2 squared. So this is the distance equals the square root of x squared plus y minus 2 squared. So that's what we're trying to minimize, is that formula right there. Again, what's the issue with that formula? The issue with that formula is it has both x's and y's in it, and we can't apply the first derivative or second derivative test if there's multiple variables. So we have to get this one equation in terms of one variable, one letter. Well, are there any restrictions? Well, of course there's restrictions. We know what y is restricted by. Y has to be 4 minus x squared. So when we look at this, we really have the distance equals the square root of x squared plus, well, then it would be 4 minus x squared minus 2 quantity squared. This is going to turn into a mess really, really quick, so bear with me. But let's take a look at this. This would be the distance equals the square root of x squared. Now let's look at this. We would have 4 minus 2. 4 minus 2 is 2, so this is 2 minus x squared quantity squared. I'm going to FOIL that out now. That's the square root of x squared. 2 times 2 would be 4, so this would be plus 4. Then it would be minus 2x squared minus 2x squared, so that's minus 4x squared. And then it would be minus x squared times minus x squared, which would be plus x to the 4th. So putting this all in proper order, this is the square root of x to the 4th. We have x squared minus 4x squared, so that's minus 3x squared, and then a plus 4. So I'm ending up with the distance formula being the square root of x to the 4th minus 3x squared plus 4. And that is what I want to minimize. So how do I minimize that? Well, I need to find the derivative. So I'm going to do that over to the left to get a little more room. The derivative of that requires the chain rule. Remember, square root of is the same thing as that raised to the 1/2. So it's going to be 1/2. The inside remains the same. X to the 4th minus 3x squared plus 4 to that power minus 1, so that would be negative 1/2, times the derivative of the inside. So drop the power, inside stays the same, power minus 1. Now we need the derivative of the inside. Well, the derivative of x to the 4th minus 3x squared plus 4 is 4x cubed minus 6x. Let's put this all together. On top, I would have a 4x cubed minus 6x. On bottom, I'd have 2, and then I'd still have a square root of x to the 4th minus 3x squared plus 4. I do notice that I can factor out a 2 in the numerator, so when I do that, I'd have a 2x, right? So if I factor out a 2x, I'd have 2x squared minus 3 on top, and on bottom, I have 2 times the square root of x to the 4th minus 3x squared plus 4. I notice that my 2's simplify, so it looks like the most simplest form of the derivative I'm getting in factored form is x times 2x squared minus 3 all over the square root of x to the fourth minus 3x squared plus 4. Why do I care about that derivative? Because I need to find my critical values. How do I find the critical values? I set the derivative equal to 0, and I set the derivative undefined. When is this derivative equal to 0? Well, it's a fraction, so that would be when the numerator, which is x times 2x squared minus 3, equals 0. That would give me x equals 0. Set 2x squared minus 3 equal to 0. I'd have 2x squared equals 3. Divide both sides by 2 and take the square root, and you'd have x equals plus or minus the square root of 3 halves. You could look at it as 3 root 2 over 2, which is perfectly fine. I don't care about that, but I'm just going to look at it as x equals plus or minus the square root of 3 halves. These are my critical values so far. That's where the derivative is equal to 0. We also want to consider where is that derivative undefined. Well, that would be where the square root of x to the fourth minus 3x squared plus 4 equals 0. You would square both sides and you would have x to the fourth minus 3x squared plus 4 equals 0. And what you can quickly do is convince yourself that this never actually happens. What you could think about is u substitution with u being x squared, if you remember those tricks right there. This does not factor. You could throw it into the quadratic formula. You would get no real numbers, so you just have irrational answers here. This never happens. This is never undefined. So the only critical values that we need to consider are plus and minus the square root of 3 halves and 0. We need to prove which one of these is minimum, which one of these is maximum, but really what we wanted in this problem was to minimize. But we need to prove that it is an actual minimum, and the only way we can do that is through the first derivative test or the second derivative test. Well, I don't know about you, but looking at that derivative, I do not want to take the second derivative of this nasty thing. So what I'm going to actually do on this problem is I'm going to find use the first derivative test. So the first derivative test, we need to prove that it minimizes. I'm going to use the first derivative test. The first derivative test, I'm going to look at these values. So I have negative the square root of 3 halves. I have 0. And I have positive the square root of 3 halves. And just to give me an idea here, I'm going to do the square root of 3 halves in my calculator, just to give me an idea mathematically. What number are we looking at? It's about 1.222, 1.22, and so on. So negative 1 and 1 lie in those ranges. I'm just thinking about test points, okay? So my first interval is negative infinity to negative square root of 3 halves. Second interval is negative square root of 3 halves to 0. Third interval is 0 to root 3 halves. The square root goes the whole way. And the last one is root 3 halves to infinity. Okay? I know my derivative at these points is equal to 0 at all 3 of these points. I know all 3 of these points are in the domain of the function, so if it changes from increasing to decreasing, it's a relative max, and if it changes from decreasing to increasing, it's a relative minimum. So I need to plug these numbers into my derivative. I can use any form of the derivative I want, but I'm going to use the most simplified version that we ended up with, which was x times 2x squared minus 3 all over the square root of x to the fourth minus 3x squared plus 4. I apologize for the handwriting and sloppiness there, but that's what it is. I need something in the first interval to the left of negative root 3 halves. How about negative 10? Something in the second interval in between negative root 3 halves and 0. How about negative 1? In between 0 and root 3 halves. How about 1? And to the right of that, how about 10? Notice on the bottom you're taking a square root, and that number has to be positive every single time, which it would be, as we discussed earlier. So all I have to do is plug this into the top. So negative 10, my first factor would be negative. 2 times negative 10 squared minus 3 is positive. A negative times a positive over a positive is a negative, so that entire first interval has to be negative. Negative 1, my first factor would be negative. 2x squared minus 3 would actually be a negative number, and a negative times a negative over a positive is actually positive, so the next interval is positive. 1, my first factor is positive. 1 squared times 2 minus 3 is a negative. Positive times a negative over a positive is negative. In my last interval 10, I'd have a positive. 10 squared times 2 minus 3 is a positive. Positive times a positive over a positive is positive. Sorry for going so fast during this. And so what do I know? I know my original function f of x on the first interval is decreasing, second interval is increasing, then back to decreasing, then back to increasing. I know because these points are in the domain, and this is the first derivative test, that at x equals negative root 3 over 2, I have to have a minimum. At x equals 0, I have to have a local maximum. And again, at root 3 over 2, I have to have another minimum. So I have used the first derivative test to prove that these are minimums, but I do actually need to find the y values of these points. And if you remember, y was equal to 4 minus x squared, right? And I'm looking at the values of negative root 3 over 2 and positive root 3 over 2. So my y values here would be 4 minus, well, root 3 over 2 squared is 3 halves. So that's 4, which is 8 halves minus 3 halves. So I'm getting a value of 5 halves for each of my y values. So that tells me the negative root 3 over 2 comma 5 halves and positive root 3 over 2 comma 5 halves. Both of those are the closest points where we have minimized the distance to the graph of the function y equals 4 minus x squared to the point 0, 2. So there's their answers right there. There's two of them. Negative root 3, sorry, I need that square root, over 2 comma 5 halves, and root 3 over 2 comma 5 halves. Nasty numbers. But it is what it is. We were able to find our derivative, our critical values, and use the first derivative test in this case to prove that those are actual minimums. So that's just one problem. Now let's move on to example 3 and see what we got there. Example 3 says a rectangular page is to contain 24 square inches of print. The margins at the top of the page are to be 1.5 inches, and the margins to the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So they want to use the minimum amount of paper. They need 24 square inches of print, and they have restrictions on the margins. So what dimension should they make this page? So what are they doing? What they've decided to do, if you look at this, is they labeled X the height of the text, not the page, and Y the width of the text, again, not the page. So what they've said is, look, on the sides we need an extra 1 inch margin, and on the top and bottom we need an extra 1.5 inch margin. So if you put that together with the margins, the height of this page would be x plus 1.5 plus 1.5, or x plus 3, and the width, including the margins, would be y plus 1, which would be y plus 2. So to find the area of this paper, which is the least amount of paper used, they want to minimize the area of paper. In this case, the area of paper would be the width, which we said is y plus 2, times the height, which is x plus 3. Again, the issue with this is it's not in terms of one variable, so we need to use our restrictions. So let's think about what the restrictions are. The restrictions are on the area of print. There must be 24 square inches of print. And again, the print is y by x. So the area of the print, which would be x times y, has to be 24. So that allows us to simply solve for one of the variables. How about divide both sides by x, and I'd have y equals 24 over x. So what can I do at that point in time? At that point in time, I can plug that in to the original equation that we want to maximize or minimize. So here I'm going to have that my area equals, well, y was 24 over x plus 2 times x plus 3. This is the equation that I want to maximize or minimize, so I'm going to go ahead and clean this up. I'm going to distribute it. So 24 over x times x, the x's would simplify, and I'd end up with 24. Then I'd have 24 over x times 3. Well, 24 times 3 is 72, so that would be plus 72 over x. And then I'd have plus 2 times x, so that's 2x. And then plus 2 times 3, which would be plus 6. So the area is equal to, well, that's 72 over x plus 2x plus, 6 plus 24, what is that, 30? Okay. So that's my original area function, but I wanted to find the derivative of that because I want to maximize it or minimize it, right? So let's find the derivative of that, a prime. A prime would be, well, the derivative of 72 over x, that's x to the negative 1, so that would be negative 72 over x squared. The derivative of 2x is just 2, and then the derivative of 30 is 0, so that's what that is. Let's set this equal to 0, so I'm going to subtract 2 from both sides. I'd have negative 72 over x squared equals negative 2. Multiply both sides by x squared, so I have negative 72 equals negative 2x squared. Divide both sides by negative 2, and I'd have x squared equals a positive 36. Nice, we got some good numbers finally. So this would give me x equals plus or minus 6. In this case, we don't need to worry about negatives. We only need to consider the positive, which is x equals 6. Again, all we have shown is that this is a critical value. We have not shown that this is a maximum or a minimum yet. So what do I need to do to prove that it's a maximum or a minimum? So prove it is in this case, we want to minimize it, right? We wanted to minimize the area. I need to choose, do I want to use the first derivative test or do I want to use the second derivative test? Well, this isn't too hard to find the second derivative, so I'm going to go ahead and use the second derivative test. So if I look at a double prime of x, negative 72 over x squared, that'd be negative 72x to the negative 2. So negative 72 times, it would be a negative 2 when you bring that exponent up, would actually be a positive 144, and then that would be x to the negative 3. X to the negative 3 is the same thing as over x cubed. So my second derivative would be a positive 144 over x cubed. Again, the derivative of 2 is 0, so I didn't worry about that. So what we need to do is plug in, for the second derivative test, plug in the critical value 6. So this would be 144 over 6 cubed. I have no idea what that is, but I do know it's positive. And because it's positive, the second derivative is positive, that means it's concave up. Because it's concave up and a critical value, that means that point must be a minimum. Okay, so that point is a minimum. So we have proven that it is a minimum. Now let's go back and ask, what the heck did they actually ask for? We know that x needs to equal 6 to minimize it, and it says what dimension should you make this page. So we know, so x equals 6 is a minimum. We need to find out what y is. If we know x equals 6, we know y is 24 over 6. Well, 24 divided by 6 is 4, so we know that y has to be 4. So what dimension should they make the page? A lot of people are going to think, okay, make the page 6 inches by 4 inches. But I want you to be very, very careful. 6 inches by 4 inches is not, absolutely not the dimensions of the page. That's the dimensions of the writing. So let's look at the dimensions of the page. We would have x plus 3 as the height. Well, that would be 6 plus 3, which would be 9. And then we would have y plus 2. Well, that would be 4 plus 2, which would be 6. So what dimensions should they make the page? You got to be really, really careful on this problem. The dimensions that they should make the page would be 9 inches by 6 inches. 9 inches by 6 inches. Again, a lot of students would have done all that work beautifully, but they would have written 6 inches by 4 inches, which is the dimensions of the writing, not the dimensions of the page. So be very careful with that.